All right, welcome everyone. So another good one today. We're doing more power series. So takes a little bit of practice. We're just going to be looking at a few more examples with these. Really, power series, it ties together a lot of what we've been doing so far, especially with sequences and series. So let's look at example 3 here. So we're going to find the radius of convergence and the interval of convergence for this power series. So it's x to the power n over 2n factorial, and it's the sum here from n equals 0 to infinity. All right, so if we remember back, the interval of convergence is really just the domain for this function. What x values can we plug in where we actually get a finite sum? What x values can we plug into this where the series converges? If we plug an x value in and we get that the series diverges, well, then it's not in the domain, it's not in our interval of convergence. So that's what we're trying to find here, is essentially what x values can we plug into this where we can actually do the sum. All right, so let's remember how this starts. So first step, normally we use the ratio test. Sometimes if everything was raised to the power n, we might do the root test. So we're going to do the ratio test. We're going to set it up. All right, so what is the ratio test? Well, we start with that gadget an plus 1 over an. And an here is just the general term of our series. So an is just x to the power n over 2n factorial. All right, so let's write this out. And to help with this, we're going to start by writing an plus 1 first. So we'll have one fraction here, and then we'll write the reciprocal of an right next door. I think I'm missing a letter there. Reciprocal of an. Yeah, we're going to write the reciprocal of an. So you could write it as, fractions stacked on top of fractions. That's fine. I think it's a little easier if you have an plus 1 and then the reciprocal of an and you multiply. So what's the reciprocal of an? Well, it's 2n factorial on top and then x to the power n in the denominator. All right, so what's an plus 1? Well, we look at an, and we just replace, each time we see an n, we replace that with n plus 1. So what is this going to look like? Well, we're going to have x to the power n plus 1 on the top, and then we'll have 2 times n plus 1 factorial. We're going to have to do some work with that factorial. Actually, this one too, just to kind of picture what these things look like. All right, so that's just the ratio test setup. Now we want to simplify this down. So the usual drill with ratio test is to line up the fractions, match like terms. So we're going to move things around. We'll have x to the power n plus 1. And then this x to the n, we'll move it to this first fraction. And then we'll move the factorials to the second fraction. We're just splitting things up. Everything's multiplication here, so we can do that. So then we'll have 2n factorial over, and then if we do the multiplication here, this will be 2 times n plus 1, so it'll be 2n plus 2. So it'll be 2n plus 2 factorial. All right. So now we want to simplify. And we can simplify these powers of x. So let's do that. So there's n plus 1 copies of x in the numerator. There's n copies of x in the denominator. So all but one of the copies of x are going to get canceled off. So we'll have one copy of x that'll still be left over. All right, now we got these factorials to deal with. And normally with factorials, it helps to just try and write them out. So let's start with the more complicated one. Let's write that out. So what is 2n plus 2 factorial? Well, you can think of factorials a few different ways. You can start at 1 and multiply up until you get to this number here. Keep multiplying by integers. Or you could start with this value and kind of work your way down. So same thing. So let's start with 2n plus 2, and then we're just going to work our way down until we get down to 1. So if we're starting at 2n plus 1, the term that comes after, well, technically before, would be 2n plus 2. Then we go down an integer, so we go down to 2n. Then we go down to 2n minus 1, and we would just keep working our way down like this until we get down to, 3 times 2 times 1, and then we would stop. So this would be 2n factorial here. Now, when we look at this, what is 2n factorial? Well, 2n factorial, we would start at 2n, and then we would go down 1, and we would keep multiplying until we get down to 3, down to 2, down to 1. So hidden right here is 2n factorial. So a lot of times with factorials, especially more complicated ones, it does help to write them out. So we have this 2n factorial. So we're really thinking of this as 2n plus 2 times 2n plus 1 times 2n factorial. So that's going to help us simplify this fraction down. So let's put that in. So we're going to have x times 2n factorial over 2n plus 2 times 2n plus 1 times 2n factorial. And that bugs me. Let's get that a little bit more centered there. 2n factorial. There we go. All right. So now we can simplify. So the 2n factorials cancel. And what are we left with? Well, we're left with the absolute value. And while we're at it, we can split up the absolute value. So we could write this as the absolute value of x times the absolute value of 1 over 2n plus 2 times 2n plus 1. So you can always do that with absolute value. You can split it up, break it up over multiplication and division. Doesn't split up over addition or subtraction very nicely. But over multiplication you can. And this thing is always positive here. So we could really drop the absolute value sign. So the ends are always positive. So this fraction here is always positive. So we can drop the absolute value. All right, so this is the ratio test setup. We looked at this gadget an plus 1 over an, and we simplified it down. And this is about as far as we could go here. Now, the next step with the ratio test is to actually calculate the limit of that. So let's see what happens. All right, so let's try that. So that's step 2 here. We're going to actually do the ratio test limit. So the limit of an plus 1 over an, absolute value as n goes to infinity. Let's use our simplified version now. So this was absolute value x times 1 over 2n plus 2 times 2n plus 1. And when we're doing this, we're doing the limit as n goes to infinity. So n is the thing that is changing here. X, even though it's technically a variable, we're viewing x as a variable here, in the context of this limit, n is the thing that's changing. So x is actually just a fixed number right now. It's a fixed number. So when we have a fixed number, it's a constant, we can move it in front of the limit sign. And you actually have to move it in front of the limit sign. There we go. So why can we do that? Normally, if we're doing the limit as x goes to infinity, no, you can't do that. You can't move the x outside of the limit. But it's the limit as n goes to infinity. So we're viewing x here as a fixed number. Just an important point to really emphasize. All right. So we do that. We have this absolute value term in front, and then we're doing the limit of 1 over 2n plus 2 times 2n plus 1 as n goes to infinity, and this is just a c over infinity form. So we know it goes to 0. The numerator is a constant, the denominator is getting really big, it's a c over infinity form, it goes to 0. So this limit is the absolute value of x times 0, which is just 0. So what we're seeing here is that no matter what x is, this limit is always 0. So for all x values, the limit of an plus 1 over an as n goes to infinity is equal to 0. And we know for the ratio test, if the limit is less than 1, if the limit of this is less than 1 by the ratio test, it converges. So this converges for all x. And that's because this limit here was equal to 0, always equal to 0. No matter what x is, if x was 1 million, the limit would still be 0. If x was 2 billion, the limit would still be 0. So no matter what x is, the limit for this ratio test gadget is always less than 1. And so the ratio test says, no matter what x is, this series is going to converge. All right, so that really answers it. So now we just got to kind of put all the pieces together here. And so we can write down our interval of convergence. And normally we do this in kind of a first pass. So sometimes there's endpoints that we need to check. So we're going to do our first pass for our interval of convergence. So if they're all x values, if all x values give us a convergent series, well then that means the interval we have is from minus infinity to infinity. Now normally there would be some finite endpoints here that we would have to check. So if this was a number or if this was a number, we'd have to check those to see if we have convergence. But because these are, this is everything. There's no endpoints that we need to check. We have all x values covered here. So let's formalize our answer. So there's really no endpoints to check. So we'll state our radius of convergence. Normally we would check endpoints, but there's no endpoints to actually check here. And then we would write down our final version. Once we went through and kind of independently verified the endpoints, we would go through and write down our interval of convergence, the final answer. but there's none. So there's no endpoints to check. We've already dealt with every single x value, so there's nothing left to do. So we get kind of lucky here. This one's not too bad. Normally you think you're close, and then you still have a lot more work with the endpoints. But fortunately for this one, there's no endpoints to check. So our interval of convergence is that it's everything. The interval from minus infinity to infinity. And so the radius of convergence is really, it gives us sort of a measure of, it's kind of think of it like half the width. So if this is an infinite interval, the radius of convergence is going to be infinite as well. So r would be, we say r is equal to infinity here. All right. So this is an example really where every single x value works out. So we get this interval of convergence that's it's the real numbers, all real numbers. Let's try another example where we have to check the endpoints. So normally, you're feeling like you're getting close, and then you have these endpoints to check, and then it's a bit more work. So let's see an example like that where there's a little bit more. Let's look at example 4. So we're going to do the radius of convergence and the interval of convergence for this power series. So it's the sum from n equals 0 to infinity of -1 raised to the n minus 1 times 3 to the n over 2n plus 1 times the x minus 1 to the power n here. We're going to start this off the same way though. So we're going to start with our ratio test setup. All right, so let's do the an plus 1 over an. And everything here is an. So this is what an is. And this is going to be kind of big. So let's put, hopefully I'll leave enough room. So we're going to do an plus 1 first, and then we'll do the reciprocal of an over here. And let's write that one out first. So the 2n plus 1 is in the denominator, so that's going to go into the numerator. And then everything else is going to go into the denominator because we're doing the reciprocal. So we'll end up with -1 to the n minus 1, 3 to the n, and then x minus 1 to the n. We're multiplying by the x minus 1 to the n, so that can actually go in the numerator. All right, so now we want the an plus 1. So basically, we're going to, wherever we see an n here, we're going to switch it to an n plus 1. So just kind of go through and just think, wherever you see an n, change it to an n plus 1. So for this power of -1, when we change that n there, it'll be n plus 1 minus 1. So we're just going to end up with -1 to the n. Then we're going to have 3 to the power n. But if we change that to an n plus 1, we'll end up with 3 to the n plus 1. And then same thing for our power of x here. It's going to be x minus 1, and then raised to the n plus 1. So we've just changed that n to an n plus 1 here. And then finally in the denominator, we're going to have 2 times n plus 1 plus 1. And remember, we're going to have to distribute that 2. It's going to multiply everything here in this n plus 1. All right, so there we go. Now comes the fun part. We get to match things up and simplify, cancel. So let's do that. So let's get all the -1s together in a single fraction. So we'll have -1 raised to the n over -1 raised to the n minus 1. Then let's get all our powers of 3. Put those in a fraction. So 3 to the n plus 1 over 3 to the n. Let's get all these n terms in their own fraction. So we'll have 2n plus 1 over 2n plus 3. So again, we're distributing here, so we end up with 2n plus 2 plus 1. That's how we get the 2n plus 3. And then finally, let's put our x minus 1 powers. There we go. So now we can just go through and cancel. So everything here is inside an absolute value. So I mean, we probably could have just canceled these off before, these powers of -1. So those are going to be gone. The powers of 3 here, there's n copies of 3 in the denominator. There's n plus 1 copies of 3 in the numerator. So everything except 1 copy of 3 is going to be left over. And not too much to do here. And then same thing, same idea with these powers of x minus 1. We're going to be able to cancel everything off, all except 1 copy of x minus 1 that's up there in the numerator. So when we simplify this down, we're going to have 3 times 2n plus 1 over 2n plus 3 times x minus 1. All inside the absolute value. And now the 3 here is positive. The 2n plus 1 over 2n plus 3 is positive. And the only thing we don't know is this x minus 1. We don't know what x is. Conceivably, this value here, x minus 1, could be negative. So when we rewrite this, when we split this up, the absolute value sign, when we split up the absolute value sign, absolute value of 3 is 3. Absolute value of 2n plus 1 over 2n plus 3 is just that. The only thing that we can't get rid of with the absolute value sign is this x minus 1 term, because we don't know what x is. Possibly this could be negative. So when we simplify, we end up with 3 times 2n plus 1 over 2n plus 3 times x minus 1, the absolute value of x minus 1. All right. So that's as far as we can go in terms of setting up this gadget for the ratio test. Now the next step will be to actually calculate the limit of that. Let's do it. Ratio test limit. All right, so we're doing the limit of an plus 1 over an as n goes to infinity. So let's fill in what we have here. We have the 3 times 2n plus 1 over 2n plus 3 times absolute value x minus 1. We're doing the limit here as n goes to infinity. Now the 3 is a constant, so we can move that in front. N is the thing that is approaching infinity, so we're viewing x as a fixed number. So we can move that in front. And then it really comes down to just doing this limit of 2n plus 1 over 2n plus 3. That's one of our kind of usual rational expressions. So we use our 1 over n method, where we identify the largest power of n in the denominator and divide everything in the numerator and divide everything by it, essentially. So when we do that, we're going to end up with 3 times the absolute value of x minus 1 times the limit of 2 plus 1 over n over 2 plus 3 over n. And when we calculate this, 1 over n goes to 0, 3 over n goes to 0, so we end up with just 2 over 2, which is 1. So our limit here is 3 times the absolute value of x minus 1. All right. So that's our limit. Let's keep that in mind. And let's think about what the ratio test actually says. So the ratio test tells us if that limit, if 3 times the absolute value of x minus 1 is less than 1, if that limit that we just calculated is less than 1, then the series converges. Okay. If that is greater than 1, then it diverges. And if it's equal to 1, well, then the ratio test is inconclusive. So if 3 times the absolute value of x minus 1 is equal to 1, inconclusive. And this inconclusive condition is going to give us this is our endpoints that we need to check. All right, so let's first figure out what our first pass for our interval of convergence is. It's not going to be our final answer, but it's on the way to getting the answer. So let's do our first pass for our IOC, our interval of convergence. So we start with where the ratio test tells us we're going to have convergence when this limit is less than 1. So we start with 3 times the absolute value of x minus 1 is less than 1. And we want to write this as, we want to get rid of the absolute value sign to see what the interval is here. So let's divide both sides by 3. So this inequality is true if and only if the absolute value of x minus 1 is less than 1/3. So just divide both sides by 3. Dividing by a positive number keeps the inequality the same. And now at this point, when we've solved for this absolute value term on the left, now we can kind of split this up and write it as sort of like a double inequality. So we can write negative 1/3 on the left is greater or is less than x minus 1. So x minus 1 there in the middle. And then greater than 1/3 or less than 1/3 on the right side. So when we have this absolute value expression, absolute value of x minus 1 is less than 1/3, we can really write that as sort of this double inequality where x minus 1 without the absolute value sign is greater than the negative value, negative 1/3, but less than the positive value, positive 1/3. And then we solve for x, try to get x by itself in the middle. So we add 1 to both sides, and then we get 2/3 on the left, and we get 4/3 on the right. So our interval of convergence, at least our first pass, we still need to check the endpoints, is what this is showing is that we're dealing with the interval from 2/3 to 4/3. This is potentially our interval of convergence. It's not our final answer yet, though. We still need to check the endpoints. Because we know at the endpoints, what happens at the endpoints, well, the ratio test is inconclusive. So at 2/3, you plug 2/3 in here, you would get it's inconclusive. 4/3, you'd plug 4/3 in here, you'd get it's inconclusive. So we still need to check these endpoints. But we have a general idea what our interval of convergence looks like. And this is enough to actually figure out our radius of convergence. So the radius of convergence is essentially half of the width. So the radius of convergence, the width of this interval is 2/3. You just subtract the endpoints, 4/3 minus 2/3, and then it's just half of that. So it's just half of this width here. So 4/3 minus 2/3 is 2/3. Divide that by 2, you get 1/3. Now, we can also see the radius of convergence right here. So if you're dealing with this inequality with this absolute value sign and you solve for that absolute value term and you have just an x or x minus a here, that constant on the other side, that's your radius of convergence. So this is also our radius of convergence. So you can kind of see that from a few places. But I think it's a nice way, at least to check your answer here, is to just look at the width of your interval, and it's half of it. All right, so now we have an idea for our interval of convergence. We've actually found the radius of convergence. Now we actually need to check the endpoints. So let's do that. So that's the next step. Step 5, check endpoints. And there's 2 endpoints we need to check. So let's start with x equal to 4/3. And what we're going to do is we're going to plug this in to our power series. So when we do that, we get the sum from n equals 0. Our coefficient terms are going to stay the same. And then wherever we see an x, we're going to change that to 4/3. So we end up with 4/3 minus 1 raised to the power n. All right, so let's clean this up a little bit. Let's simplify this. So when we do the subtraction here, we end up with 1/3 raised to the n. And I'll put that in the numerator, 1/3 to the n. And then all over 2n plus 1. And we see we have a 3 to the power n and a 1/3 raised to the power n. So those are going to cancel. And what we're left with here is the sum from n equals 0 to infinity of -1 raised to the n minus 1 power over 2n plus 1. And that's an alternating series. So we got to test that with the alternating series test. So we get it all. So let's do the alternating series test. So the first step for our alternating series test is to figure out what Bn is. So it's everything without that alternating piece. So Bn is 1 over 2n plus 1. It's everything that's here except that alternating piece, that power of -1. And so what do we need to check with the alternating series test? We need to check that the limit of Bn as n goes to infinity, we need to check that it's equal to 0. So let's just do that. Yeah, that's a c over infinity form. So that is equal to 0. Good. The other thing we need to check is that Bn is a decreasing sequence. So we need to check that Bn plus 1 is less than or equal to Bn. All right, so let's actually check that. So this is true. Let's just fill in what Bn plus 1 is and Bn is. So Bn is 1 over 2n plus 1. What is Bn plus 1? Let's go through the same process that we saw. Let's change that n to an n plus 1. And what do we get? We get 1 over 2 times n plus 1 plus 1. So this is true if and only if this is true. And I guess we could have an equal here. Let's simplify this. So 1 over 2n plus 3 is less than or equal to 1 over 2n plus 1. So what we want is true if and only if this is true. And then we can cross multiply here because everything is positive. So it doesn't change the inequality at all. So we get 2n plus 1 is less than or equal to 2n plus 3. And then here we have, this is clearly true. So because this statement is true, we can work our way back and we get that our inequality is true. All right, so both conditions are met for our alternating series test. So what that shows us is that this series is convergent. So we have convergence at x equal to 4/3. So let's tuck that away. We're gonna, when we write down our final version of our interval of convergence, we're gonna need this. So we know that when we plug x equals 4/3 in, we get a convergent series. The ratio test was inconclusive, so we had to do something else. So in this case, we had to use the alternating series test. All right. Now we need to check the other endpoint. Whew. So let's do x equal to 2/3. Let's plug that in. So we're going to get -1 raised to the n minus 1 times 3 to the n over 2n plus 1 and 2/3 minus 1 raised to the n. Now this is going to be -1/3. So we're going to have this -1 to the n minus 1 times 3 to the n, and then we're going to have -1/3 raised to the n. And this is all over our 2n plus 1. Now we can split this up. This -1/3, we can split that up. So let's look at what's happening here. So we have, looks like we're going to have some powers of 3 that might be able to cancel, but then we also have this negative in here. So let's just look at what's happening with this numerator. So we can write -1/3 raised to the n as -1 raised to the n times 1/3 raised to the n. And so what happens when we multiply -1 raised to the n and -1 raised to the n minus 1? Well, if n is even, this is going to be +1, but this is going to be -1. And if n is odd, well, this will be -1, and this will be +1. So no matter what happens here, one of these is going to be negative, the other one's going to be positive, so we're always going to end up with -1. No matter what n is here, one is positive, the other is -1. So we're always going to end up with -1 here. So when we put all this in, this -1/3 to the n, we can split it up so that we have -1 to the n times 1/3 to the n. And when we multiply that, let's multiply the powers of -1 together. We're always going to get -1. And then the 3n times the 1/3 to the n, those are just going to cancel. So we always end up here with the sum from n equals 0 to infinity of -1/2 to the n plus 1. And this negative here, we can really think of this as, we can really bring the negative out in front. This is just a constant. So we can really just investigate the convergence of 1/2 to the n plus 1. So let's get that negative out of there. There's no n attached, so we can move it in front. And let's look at the convergence of this. And to do this, looks like a p-series. It's not quite a p-series because we have some extra stuff going on here in the denominator. So we have to use one of our comparison tests. So let's try, what are we going to try here? Let's try the limit comparison test. Kind of a little bit less to check there. So what are we going to compare this to? It's kind of the first part. We need to find our comparable series. So we're an here is 1 over 2 to the n plus 1. And, well, yeah. And then our comparable series, Bn, that's going to be just the dominant terms. So it's just going to be 1 over 2 to the n. And we know that this, when we look at the sum of these, this is a convergent series now, convergent p-series. Or divergent p-series, rather. And the p-value here is 1. So, and that's less than or equal to 1. So we know a p-series is divergent if the p-value is less than or equal to 1. So we're going to do the limit comparison test. So we're going to do the limit of an over bn as n goes to infinity. And let's write this out. So we'll do the limit of 1 over 2n plus 1 times 2n over 1, the reciprocal here. Again, it's a power of, it's one of our rational expressions. So this is an, this is the reciprocal of bn. This is one of our rational expressions. So we can kind of consolidate and then divide by the highest power of n in the denominator. So kind of our usual standard method here. And so we end up with 2 over 2 plus 1 over n, which ends up being 1. And the fact that our limit comparison test, the fact that this limit is greater than 0, tells us that they both do the same thing. So that's what our limit comparison test says. It says if you calculate the limit of an over bn and you get something that's not 0, well, then they both do the same thing. So in this case, sigma bn here, our comparable series, is divergent. So that means sigma an here, the one we were actually interested in, is divergent as well. So that means we have a divergent series here. All right, so this is a divergent series. So when x is equal to 2/3, the series is divergent. So we started with x equal to 2/3. We plugged it in. We got a divergent series. So now we've done it. We got all the endpoints checked. So we have our left endpoint 2/3. We've checked that one, showed it was divergent. We checked the other endpoint 4/3. There we actually saw that it was convergent. And now we're ready to just kind of finally answer, what is the radius of convergence? So our radius of convergence, we go to our interval here, and at the endpoints, if the endpoint was divergent, we leave it a parentheses. If the endpoint was convergent, then we put our brackets, meaning we want to include that endpoint in our interval. So the interval of convergence, we can finally answer it here. So we saw it was divergent at 2/3, so we're going to keep that open. We don't want to include that endpoint because it's divergent. But at 4/3, everything worked out nicely. So gotta squeeze it in here. But at 4/3, everything worked out nicely. We did get a convergent series. So we're going to use the closed bracket here to indicate we want to include that endpoint. All right. So that's a good breaking point here. These examples take a little bit. Probably look at one more, maybe one more next time. So yeah, these really do tie everything in together. So all of the tests that we've been looking at, ratio test, all of the other tests, limit comparison, alternating series, all the tests kind of come into play. So you do the ratio test to get most of the interval, and then for the endpoints you have to use one of the other tests or two of the other tests. So you're really putting a lot of our topics here together. All right, so we'll try a few more examples next time. So we'll see you then. Bye-bye.